This is section 7.4. We're still working with our Laplace transforms. And now we're going to start working backwards, looking for an inverse equation or an inverse function to the Laplace transformation. So here, let's start with an example. If we were asked to solve y double prime plus y is equal to t, and we were given two initial values, y of 0 is equal to 0 and y prime of 0 is equal to 1. We may have any number of ways to try to solve this, but let's look at this through a Laplacian lens. We're going to take the Laplace transform of both sides of this equation. Now the right side, we've gone over this enough, we know that that is equal to 1 over s squared. As for the left side, we can break it up using our linearity, so it becomes the sum of two Laplacians. And when we see this prime, this double derivative here, we have from our last video a trick for that as well. We can break that down as s squared. Remember that this 2 comes from there being two primes here, times the Laplace of the original function y, minus s times y naught, minus y prime of 0. Sorry, not y naught, y of 0, minus y prime of 0, plus the Laplacian of y, which is just carried down. So we have a bit more information we can solve here because we know that y of 0 is equal to 0. And we know y prime of 0 is equal to 1. So we can plug those in. This s just disappears because it's multiplied by 0. So we have s squared times the Laplacian of y minus 1 plus the Laplacian of y is equal to 1 over s squared. Well, that becomes s squared Laplacian of y minus 1 plus Laplacian of y. We're just going to move that 1 to the right side of the equation. So that's how we get this plus 1 over here. And then we'll factor out the common Laplacian term to be left with s squared plus 1. We'll find a common denominator on the right, and then we will divide both sides by this s squared plus 1, trying to solve for what the Laplacian of y is. When we divide both sides by s squared plus 1, we have a common term that will cancel out, and we're left with 1 over s squared, which is a function that we know the Laplacian of, or actually the inverse Laplacian of. It's t. We know that if you take the Laplacian of t, you get 1 over s squared. So moving backwards is the same thing. Now this is a handy way to use the Laplace transform as long as we can perform an inverse function. We were only able to reach this solution because we know that the Laplace transform of t is 1 over s squared. So given a function f of s, if there is a function little f of t that is continuous from 0 to infinity and satisfies that its Laplacian transform is capital F, then we say that little f is the inverse Laplace transform of big F. And we use the usual notation. We just use the inverse notation on it. So let's use that to figure out the Laplacian transform of 3 over s squared plus 8s plus 25. First off, that's typo. It's not a 9, it's a 3. So the Laplacian of 3 over s squared plus 8s plus 25 is equal to, we can factorize this bottom in a nice way to become s plus 4 squared plus 3 squared. But of course, it wouldn't be clear why we're doing that unless you knew that the Laplacian of sine bt is equal to b over s squared plus b squared, as we solved in the last video. So here it's starting to actually take shape. We have that b must be equal to 3. We've got our b squared in the denominator. There's a little bit of a problem here though, because s squared is not the same as s plus 4 squared. But here's where we use our translation rule from the last video, where s minus a can replace s if you multiply by e to the at. Well, here we're not subtracting, we're adding. So it's not going to be e to the positive 4t, it's going to be e to the negative 4t. And that's how we get our answer. It's e to the negative 4t times sine of bt, but the b value is 3. So sine of 3t. So assume that, now these are rules that we've talked about before, our linearity, our constant that can be factored out. But the point here is that we can also use this for the inverses. So if you have the inverse Laplace of some sum of functions, well, that's just equal to the sum of the inverse functions. And the same with factoring out a constant c. Okay, let's try to solve another one. Let's solve, the Laplacian is 9 over s minus 2 minus 1 over s squared minus 2s plus 2. What is the Laplacian of this? Well, it's already broken into this sum, so we're not going to do anything about that. So we're going to use our linearity to break it into two pieces. And then we're going to factor out this 9. So we have 9 times the Laplacian of 1 over s minus 2. Well, that's clearly 9 times e to the 2t, because it's that power of 2 that allows you to translate the s. And remember, 1 over s is the Laplacian of 1. So 1 over s minus 2 is just 1 times e to the 2t. On the right side here, we are going to factorize the denominator to make it look like our sine version. So we have 1 and we have 1 squared, which is just 1. And then we have our s squared term. Of course, it's not just s squared, it's s minus 1 squared. So we need to translate by using an e to the 1t. So that's how we get this 9e to the 2t minus e to the t times sine of t. Let's try another example. Solve the Laplacian of 3s plus 1 over s squared plus 5s plus 6. Well, we can factorize this denominator from s plus 2 times s plus 3. And then we're going to use partial fractions. So in case you're unfamiliar with partial fractions, it's a way to break up a large fraction here into a sum of smaller denominators. So we set it equal to a over 1 factor plus b over the second factor. Now we're going to multiply to get a common denominator. So it's a times s plus 3 plus b times s plus 2 over s plus 2, s plus 3. And now you can see how this fraction takes the same form as the one in the original equation. So if we can solve for a and b, we will have successfully broken up this large fraction into a sum of two smaller fractions. So we get a plus b times s, that's as plus bs, plus 3 times a plus 2 times b in the numerator, and the denominator stays the same. And we're going to set that numerator equal to 3s plus 1, the numerator in the original statement. So we can now say, well, the things multiplied by s must be equal, so 3 must be equal to a plus b, and the constants must be equal. 1 must be equal to 3a plus 2b. So we get that a is equal to 3 minus b. We can plug that into the right side equation. We get that b is equal to 8 on the right, and a is equal to -5 on the left there. So we can plug those values in. So we've simplified this larger fraction into a sum of two smaller fractions, -5 over s plus 2 plus 8 over s plus 3. Now we can calculate those Laplaces. So one missing there. So we use our linearity to break it up into two pieces. We factor out our -5 and our +8. And we're left with -5 e to the -2t plus 8 e to the -3t. And remember, that's because we know the Laplace of 1 is equal to 1 over s. And if you want to translate that to the right or left, you're going to use these e to the power of something times t. -2 will move it +2, and -3 will move it +3. Okay, we've got one final example, and this is really going to tie together everything that we've learned about Laplacian transforms. The Laplace of 1 over s squared plus s plus 1 times s minus 1 squared. So we're going to use partial fractions. And if you recall from previous courses you may have taken, there are three different types of denominators that may show up when you're taking these partial fractions. As we had in the previous question, sometimes you just see things like s minus 2, and then you just simply put some constant a over s minus 2, and you're fine. But the other things that can happen are you can have, as we have here, an s minus 1 squared, and then we need to know what to put on that. Or you may have some quadratic that doesn't factorize. And we would need to know what to put on top of that. So our rules are for partial fractions that if you see some linear thing squared, you're just going to put an a over it to the power of 1 plus b over it to the power of 2. So that's going to be our rule whenever you see some linear thing squared. You're going to make one fraction out of the power of 1 version plus another fraction using the power of 2 version. But now we need to know how to deal with this s squared plus s plus 1. Since it doesn't factorize well, we need the numerator to express every possible numerator that could arise. And it could be that it's not just a constant. It could be something times s plus d. It could be something linear. So we're going to put cs plus d to represent all of the possible linear functions that could be in that numerator. Now that we have it set up properly, we are going to give everything a common denominator. So a must be multiplied by s minus 1 and s squared plus s plus 1 so that it has the right denominator. And then we do the same with the others. Multiply them by the proper pieces so that we get the common denominator. And then we're going to set the numerators equal to each other. We can forget the denominators for now because they're equal. So we can just set the numerators equal to each other. The left side is just 1. The right side, we actually have to multiply out every piece of this. So we have a rather long right side. And now we get a number of equations. Well, 1 must be equal to all the constant terms, so all the ones that don't have an s in them. So we have -a, positive b, positive d. So that's how we get this equation. Now on the left, there's no s term, it's just 0. So we're going to set 0 equal to everything that's multiplied by s on the right side. Well, that's b, c, and minus 2d. And the left side also has 0 s squared terms. So we're going to set 0 equal to all the s squared stuff over here. We have bs squared minus 2cs squared plus ds squared. So we get b minus 2c plus d. And then finally, we have our cube terms. Again, there's 0 of those on the left. So 0 is going to be equal to a plus c. Notice that the pieces I didn't circle canceled each other out. plus as squared minus as squared plus as minus as. And now here's the fun part of solving this system of 4 equations. So you can set this one equal to a. We can get what a is equal to in a couple of places. We're going to plug in that a is equal to b plus d minus 1 into this equation. Then plug in that a is equal to negative c, and we solve this for c, which also allows us to solve this one for a, because it's just the negative of c. Then we plug in our a and c values everywhere that we can. And we get that b is equal to 2/3 minus d. So we can plug that in for b here. And then finally reach that our solutions are negative 1/3, positive 1/3, positive 1/3, and positive 1/3. So that's a little bit of fun, just doing your substitutions, isolating and plugging them into the other equations until you solve. So now we're going to plug in 1/3 everywhere. So we're just going to keep dividing everything by 3 here. And to note what plugging in we did, we plugged these values in here. So a became negative 1/3, b became positive 1/3, and c and d were both also 1/3. So that's how we reached this point. Now we're going to use our Laplace rules, where we can break it up into a sum of smaller Laplace transforms. We can factor out that 1/3 just everywhere. And some of these are done. We can solve some of them quickly. 1/s minus 1, well, we know that's just e to the t. 1/s minus 1 squared, well, that's t e to the t. But the one on the right is going to be a little trickier. We're going to look for a way that we can get the square going on in the denominator, and we also want the numerator to look like it as well. So the problem is s minus 1 is not equal to s plus a half. Sorry, s plus 1 is not equal to s plus a half. So we're going to break this up into s plus a half plus a half, and we'll solve it in 2 pieces. So now 3/4 is the square root of 3/2 all squared. And now this was quite a bit of algebra, quite a bit of work to get this in the proper form. But remember, the form we're looking for is s over s squared plus b squared in order to get to our cos form. Now s is replaced by s plus a half. So that means we're using our translation formula to move using e to the negative 1/2. And the b value is √3/2. So that's how we show that this is our solution. And now let's look on the right. We're going to do something very similar on the right. We have 1/2 s plus a half squared, and we've still got this √3/2. This isn't taking the same form of the cos one, but it's very close. What it's actually taking the form of is b over s squared plus b squared, which we know is sine of bt. But there's a problem, because 1/2 is not equal to √3/2, but it needs to be. So we are going to have to multiply and divide that numerator by √3. So we now have our √3/2 in the numerator and the denominator, but this √3 right here is going to have to come out using our rules of linearity as a factor. When it does, we reach the proper form where we have this value being equal to this value once that √3 is taken out of the denominator. And we have s plus 1/2 is our translation on s, so it's still going to be e to the negative 1/2 t here. and sine of root 3 over 2t. And this is our final solution. So when you're doing something that may be timed, something that you may be marked on a workshop, an exam or something, there may be partial fractions, but there won't be something all this long where you have to do a couple pages of work. So I would like for you to get comfortable with partial fractions, and especially with working with Laplace transforms. But this question was certainly just made to be a way to bring everything that we knew together.